All right, class. Got a couple questions here this weekend about number 28. So maybe I will give this one a shot. And let me just read it. I will start off, though, by pointing out that PV diagrams are a powerful tool. And so oftentimes you should have the PV diagram in front of you. Now, in this problem, they give you the PV diagram, so I'm not so sure it's necessary to repeat it, but since I'm just doing the video, I'll kind of repeat it here. The other thing to keep in mind is the units that can be quite confusing at times because the units that result in energy in joules are when you're in pascals and cubic meters. Now, also for that matter, kilopascals and liters would do the same thing. But what will not do the same thing is what we have here. Because we've got volume, it looks like on the chart, in cubic meters, and pressure in atmospheres. So one of the things I'm going to make note of right away, especially since most of the time energy is in joules, and as I scan the problem, it looks like kilojoules. Okay, so that would be kilopascals in cubic meters. So I'll keep that in mind here. But here is the PV diagram so we can look at it. And then now let me read it. It says a sample of an ideal gas goes through a process shown in figure 28. From A to B, the process is adiabatic. All right, let me show you a little tool that I like. I like to just kind of write out the process because from A to B, there's a number of things that can happen. And if we're talking about the energy, there would be a change in the internal energy. Now, that change could come from heat or that change could come from work. But according to the first law of thermodynamics, the heat plus the work is the total energy added or taken away. Positive numbers when we go in, negative numbers when they come out using the sign convention by Survey, and so that's what I'm going to follow here. And so keep in mind that if I know any two of these, I've also got the third. This is just a conservation of energy statement. So there's A to B, B to C, C to D, and then technically D, I forgot to put a D here, back to A, and it's a complete cycle. And of course, then we could add them all together. And so there's a couple of things I should always point out, but I think a table like this is a helpful skill or a helpful tool into solving things. Like I said, written in this way, if I know any two, I can get the third, okay? I also know that because it's a full cycle, if I start at A and go back to M exactly at the same conditions, so the total change of internal energy must be zero. Now, maybe I added more heat and then took work out, so there's a positive and a negative here. So I know that these are going to be equal and opposite totals because it's got to come out to be zero. And that's, again, just kind of what is meant by a cycle here. You're back where you started, conservation of energy. So we know the total change in internal energy is zero. And I point that out because this first one says, it says from A to B, the process is adiabatic. Now, the definition of adiabatic is zero heat. So I'm going to put that right in there. And I call this doing the easy ones here first. Okay. Let's see. So A to B, the process is adiabatic. B to C, it's isobaric, and you can see the straight line. That means constant pressure. It's isobaric with 100 kilojoules of energy entering the system by heat. So B to C, right here, they say heat, and they say 100 kilojoules. Now, I'm going to do my energy in joules, so I'm going to put here 100,000. So that's how much goes in the process from B to C. Then it goes on to say from C to D, the process is isothermal. Okay, now again, something to remember, C to D, it's isothermal. In that case, we know the delta E is 0. We know that because the molecules of a gas, an ideal gas anyways, don't interact with each other. There's no energy associated. It's all with kinetic energy, and temperature's with kinetic energy. So if there's no change in temperature, which is isothermic, then there's no change of their energy. Now, that doesn't mean that these things here are 0. In fact, as you can see from C to D, the volume's getting bigger, so the gas is pushing outward. So from C to D, we're going to have a negative number here, and that means heat must be positive. So there must be adding heat energy, and it's losing that same energy at the same rate it's expanding. Those two are equal and opposite, which is going to give you a change of 0 during this C to D process. So C to D is an isotherm. And then from D back to A is another isobaric with 150 kilojoules of energy leaving the system. So the leaving means a negative number, and the 150,000 is the number that they're given. Okay, and so here's the question. It says, determine the difference in internal energy from B to A, or from, well, A to B. So this number here, this is what we're hunting for. Now, here's a good piece of news. As I said earlier, this has to add to 0. So if we knew these 3, and we know one of them, if we can get these other 2, we know that they have to add to 0. That would be a good approach. Now, also, we know that these 2 add together to give us that one. These 2 add together to give us that one. So really, if I could find these 2, that would give me then these 2, which I then have these 3, which would give me that question mark. So that would be perfect. And, of course, I can get that. And then I think we might be able to find these other ones. That one's kind of questionable. So we may not have enough information here to be able to find everything. I think so, though. But let me not try to do everything. Let me just try to do what they are after. But the reason this comes to mind is because this chapter focused on the equation, the fundamental idea of getting work. And it's this integral, or area under the curve. And so the B to C and the D to A were both isobaric. And they're flat lines. And so getting the area under there is actually very, very simple. So I like that. So that's the approach I'm going to take. I'm going to find the area under them. In fact, maybe I'll get an equation. I won't even bother to look at the graph. But then I get those numbers, which then gives me these numbers, which give me my question mark. Now, the reason calculating work for isobaric is so nice is because the phrase isobaric means constant pressure, and you can pull the P out in front. So notice I can only do that for a constant pressure problem. And so this little equation here for the work is technically only valid for B to C and then also D to A. Well, this is true all the time, but I guess I should have put it here. So this would only be true from B to C and D to A. This is always true. But that special step right there required the pressure to be constant. And then if I do an integral from some initial volume to some final volume, you can see I have minus the pressure. And then that's an easy integral. That's just final volume minus initial volume. In fact, this will give me a chance to pause and comment that notice if the final volume is bigger than the initial, that is if the gas gets bigger, this comes out to be a negative number. Because when final is bigger than initial, this is positive. Pressure is always positive with a negative in front, makes that whole thing negative. And that makes sense. When it gets bigger, it's losing energy. It's pushing on the environment. The gas is losing the energy as it does work on the environment. And it's also true the other way around, that if the gas gets compressed so that the final is smaller than the initial, so that'd be negative. And the negative with that negative make a positive. And so when a gas gets smaller, the work is positive, which makes sense. That means the environment is squeezing the gas. The environment is pushing on it. And so we've got our positives and negative. And so one of the key here in thermodynamics is really to keep track of when are things positive and when are they negative, and how those could be really helpful. All right, so let's calculate this number here, the work from B to C. So the work from B to C would be minus the pressure from B to C. And B to C is right here, 3 atmospheres. So maybe for the moment I'll just put 3 atmospheres, but I think I'm going to want my energy in joules. And then the final volume, and it looks like the final volume is 0.4 cubic meters. I think I wrote that down right. That would be C minus the volume at B, which is 0.09 cubic meters. All right, now maybe to make this come out to be appropriate units, I'm going to put in place of 1 atmosphere 101,300 pascals. So that when I grab my calculator here and go 0.4 minus 0.09 and get 0.31 cubic meters, I am now going to have a Pascal times a cubic meter, where a Pascal is a Newton over a meter squared, so 2 of them would cancel, and I have Newton times a meter, which is a joule. So perfect. All right, so there's the 0.31 times 101,300 and times 3. And that makes 94,209. Oh, and let me not forget the negative. Positive, 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 negative. And it makes sense. It's getting bigger from B to C, so it should be a negative work, as we said a moment ago. And let me put that in my chart up here. So this is negative 94,209 joules. So you hopefully can see how we're adding heat, a lot of heat energy. And as it expands, it's losing a lot of that energy. Not quite all 100,000, but pretty darn close. And so if I take 100, 3,000, and subtract that last answer, there is a net gain of only 5,791 joules during the B to C process. Even though we put a lot of thermal energy into it, the expanding gas is where most of that energy went, and there then is a small amount of gain of internal thermal energy, and then technically a small amount of a temperature going up. Okay, now that being said, let's also do the same thing in this D to A process. And that would be minus P times the volume at A minus the volume at D. All right, so the D to A process, here's the D and going over to A, looks like we have 1 atmospheric pressure, which I'm going to go ahead just right away, change it to pascals. And then the volume at A, 0.2 cubic meters. Minus the volume at D, which is 1.2 cubic meters. Well, that was nice, because that's just a negative 1, and negative 1 times that negative is just 1, and then of course times the 101,300 pascals. And notice it came out to be a positive, I'm sorry, pascals times cubic meters, which is a joule. And so this is 101,000. So notice this is going into the gas. So let me put that in my chart. 101,300. So that's energy being added to it as we squish it. And that would have been a huge increase in the energy, except for heat was coming out. So it was also in the process of being cooled. And it looked like more came out than went in. And so let's put here the negative 150, 123,000, and add to it the 101,300. And it looks like a lot of cooling must have gone on because we took a lot of energy out. Now, a net of this, because we did so much work on it. Okay. All right. Well, finally, we can answer this, but I'm going to make one more comment before we finish up here. And that is, if you'll notice, from A to B, the gas is getting smaller. The gas is getting compressed. That means this is a positive number. Now remember, these two add up to that. So this needs to be a positive number, which you can kind of see that now because maybe just to save room on the paper, I'll come down here, question mark plus 5,791 plus 0 plus a negative 48,700 all have to equal 0. All right, so I'm going to move this over. And so I'll do that by just multiplying by a negative 1. So that's a positive 48,700. I'll move this over, so that becomes a negative 5,791. And that leaves me with a question mark of positive 42,909 joules. So 42,909 joules. Yay! Hope that was helpful. All right, bye.